Today we will discuss about the VTU solved question paper for January 2019. So the first question is what are shock waves? Mention the characteristics and applications of shock waves. So first you are supposed to write the definition of shock waves. So already you studied shock wave is a narrow surface that manifests as a discontinuity in a fluid medium in which it is propagating with a supersonic speed. So here you have to highlight this word supersonic speed, and then here there will be some increase in temperature, pressure and density of the gas. It will happen due to the shock waves. So these are the points you have to highlight. And then two more questions are here, that is characteristics and then applications of shock waves. So characteristics, you can see the Mach number that is greater than 1.5 for the shock waves. And then this ready tube, it is operating on the principle of a free piston driven shock tube. So you should write all these points. And then application, here it is mentioned cell information, wood preservation, use in pencil industries. Okay, so all these side readings are given, but you have to explain all these things in detail, right? So then the second question you can see, that is first B, that is what are damped oscillations? Give the theory of damped oscillations and hence they discuss the case of critical damping. So first you are supposed to write the definition for damped oscillations. So you study it is a type of motion. Oscillations, it is a type of motion. It is executed by a body, and the body is subjected to both restoring and resistive forces, and the motion gets terminated with the body coming to rest at the equilibrium position in a finite interval of time. So first you are supposed to write the definition for damped oscillations, and then theory of damped oscillation. So here the resistive force equation, restoring force equation, so you are supposed to write. Okay, so then you can see up to equation 5. So that is m d square x by dt square. So equation 5, that is equation of motion for damped vibrations. Then you have to continue up to that final equation. So that is a general solution for damped vibrations. So theory of damped oscillations completely you have to write. All these each and every steps, each and every point. Okay, so you have to write. So then one more question is there, that is regarding case of critical damping. So critical damping condition, we know B square equals omega square. So this condition you are supposed to write, and this B is the damping constant, so that is equal to the natural frequency of the body. So this is the condition for critical damping, and then you are supposed to write the derivation part also, right? Then 1C, so that is one problem is given here. So you can see that is a free particle is executing simple harmonic motion. Okay, and then the time period, that is 25 seconds is given. Then 5 seconds after it crossed the equilibrium point, its velocity is found to be 0.7 meter per second. So, okay, so here we should find out the displacement at the end of 10 seconds and also the amplitude of oscillations. So here the question is amplitude of oscillations, A equals, that one we have to find out, and the displacement at the end of 10 seconds. Okay, so first we have written all the given data here, time period 25 seconds, velocity that is 0.7 meter per second. Okay, then time t1 equals to 5 seconds, it is written. So here the system is going for simple harmonic motion. So right, so here first you can see the solution, you can see angular frequency we are finding. So angular frequency omega, that is equal 2 pi multiplied by linear frequency f. So f, that is the inverse of the time period, so 2 pi by t, and the time period is given here, that is 25 seconds. So here then we are applying the equation, simple harmonic equation, x equals a sin omega t. Then we are differentiating this equation, so dx by dt, so then you can see that is velocity only, dx by dt is velocity only, so that is equal to a omega cos omega t. So velocity value we have substituted, then amplitude we got it. Then in this displacement equation we are finding x equals 5.3 meters. So then the second A you can see, that is define simple harmonic motion and then mention the characteristics of SHM and give one example. So the definition of simple harmonic motion, that is, it is an oscillatory motion of a body where the restoring force is proportional to the negative of displacement. Okay, so then the characteristics of SHM, so these are the these points you have to highlight. Type of, it is a type of periodic motion, then oscillating system must have inertia, so there is a constant restoring force, then the acceleration, it is proportional to the displacement, negative of the displacement. So then SHM, it is represented by this equation x equals a sin omega t. Then one example it is given here, a pendulum set for oscillations. So in your text some more examples they have given. So any one example here you are supposed to write. Then the second one, next question, that is regarding the reddish shock tube. Okay, so you can say, write with a neat diagram, explain the construction and working of reddish shock tube. So the next one you can see here. So the next one, that is explain the construction and working of reddish shock tube. So here first you have to do the diagram for a reddish shock tube. So diagram you have to perform, then the construction and working you have to explain. So in the construction you can see, so here the diameter of the tube, that is 30 millimeter and length is 1 meter, and then each cross sections it is of 50 centimeter, and then the diaphragm thickness you have to mention. Okay, so here the diaphragm is made up of aluminium or paper, and the digital pressure gauge it is there, then the piezoelectric sensors. So these things you have to highlight. So then you can see working, so working is mentioned here. Then conservation of mass, one more question is there, so that is regarding the conservation of mass, energy and momentum. So all these equations it is mentioned here, right? So then the question 1C you can see, the question, that is a mass of 0.5 kg, it causes an extension. So read out the question. Then here we have to find out the force constant for the spring, and then angular frequency, then the time period. So the restoring force, that is F equals mg. So mass and acceleration of gravity, it is multiplied here. Then the force constant k equals F by x. So then we are substituting all the data here. Then omega, that is square root of k by m. So then 18.1 we are getting here. Then the frequency, that is equal to omega by 2 pi. Then the time period we are calculating as 0.35 seconds. So then module 2 you can see, that is given state and explain Hooke's law, define elastic and plastic limits. So Hooke's law, it is written here, that is a strain in a solid is proportional to the applied stress within the elastic limit of that solid. So here it is written stress is proportional to strain within the elastic limit, and then the limits of plastic and elastic it is given here. Okay, so then 3b, that is define Young's modulus of the materials, and then derivation for the Young's modulus. So Young's modulus definition, that is the ratio of longitudinal stress to the linear strain. So that is units Newton per meter square. So then the derivation of the Young's modulus by single cantilever method it is given. So up to this y equals w, you have to do the diagram also. So first you have to perform the diagram, then you do this derivation part also. So up to y equals w l cube by 3 y naught. So here y naught, small y, that is the depression ig. Okay, so that is a geometrical moment of inertia. So up to that you have to write. Then 1c, that is torque. So calculate the torque required to twist the wire of length, it is given here. Okay, then rigidity modulus, these things are given. So we know the equation, tau equals c multiplied by theta, and c is the couple per unit twist. So then we are substituting here, c equals pi n r power 4 by 2l. So n is given here, small n, that is rigidity modulus 8.3 into 10 power 10. Okay, so then couple per unit twist we have calculated from equation 3. Then we are substituting in equation 1. Then the torque we are getting is 1.98 into 10 power minus 4 Newton meter. Then 1c, that is you can see that is definition. 4a, that is what is bending moment, and then mention various types of beams and their applications. So here any 4 applications they asked. So first you have to write the definition for bending moment. So the moment of the applied couple subject to which the beam undergoes bending longitudinally is called bending moment. So then various types of beams are mentioned here. So that is simple beam, continuous beam, cantilever beam, and then fixed beam. So then applications, some applications it is written here. Okay, so then read out the question. Then 3b, that is define Young's modulus of the, what are the types of elastic moduli, and then derive the relation between y, k and sigma. So 3 different types of elastic moduli is given here, Young's modulus, bulk modulus, and then rigidity modulus, it is given here. So then the relation between k, y and sigma, it is you are supposed to derive. So it is given in page number 111 in your text, Basavaraj book. So then 3c, the question is calculate the force required to produce an extension of 1 millimeter of in a steel wire of length and diameter is given here. So here force we have to find out, and here Young's modulus it is mentioned here. So here you see that is Young's modulus equation, already we know that is the ratio of longitudinal stress to the linear strain. So that is F by A by X by L only. So that equation 1 we have written here. So then from here we should derive F equals force. Okay, so then force, after substituting all these given data, we are getting 78.54 newtons. So then the next one, that is you can see here 5c. So 5a, that is what is numerical aperture, and then derive the expression for the same. So here numerical aperture, that is light gathering capability of the optical fiber. Then the derivation for numerical aperture. So for that first you have to perform the diagram. Okay, so do the diagram, neat diagram, and then arrow marks. So all these light diagrams should be mentioned with arrow marks only. So then after applying this Snell's law at the entry point and also at the interface between core and cladding, so we are getting the equation for sin theta naught or numerical aperture. So that is equal to square root of n1 square minus n2 square. So first you have to do the diagram, a neat diagram, and then you have to write all the derivation part. Okay, so up to numerical aperture equals square root of n1 square minus n2 square you should write. Then the next one, that is it is based on state and explain Maxwell's equation for electromagnet, and then starting from the equation, Maxwell's equation, deduce the wave equation. So first it is written Maxwell's equation for electromagnetic field. So 4 equations it is written here. Then from this by using this Maxwell's equation, we are deriving the equation wave equation for a plane wave in free space. So up to del square minus mu e, that is permeability, and this is the permittivity. Mu is the permeability of free space and this is the permittivity of free space. Okay, so up to that you have to derive this equation. And then phi c, that is a vector, it is given here. Then it is given, a vector is given and it is a solenoidal. Okay, the question is like that. Then from this data, from this question, we should find out a constant c value. So in this equation, a constant value c is there, so that value we have to find out. So here in the question it is given a vector to be solenoidal, so it means del dot a vector equal to 0. Okay, so then a vector we have written. So then you can see a vector, that is so del dot a vector means so dou ax by dou x plus dou ay by dou y. So we can write like that. So if we are differentiating the given data, we are getting 2 plus c. So del dot a vector we are getting as 2 plus c, then that is equated to 0. So then we are finding c equals minus 2. So then 6a, that is explain the types of fiber losses. So we studied about different types of fiber losses. So that is attenuation. Okay, so there will be some reduction in the intensity of the light signal while it is propagating through the optical fiber. Okay, so 3 factors are there. So that is absorption losses, scattering losses, and then radiation losses. So you have to explain all these things in detail. And then 6b, that is state and explain Gauss divergence theorem and mention the Stokes theorem. So the statement of Gauss divergence theorem is given here, so with the equation, and then proof also it is given here. So all these steps in the derivation part, so you should mention all these steps. Okay, and then the Stokes theorem is given. Stokes theorem definition it is given here with the equation. So that is integral del cross f vector into ds equals closed integral f vector dot dl. So then the next one, that is the refractive indices of core and cladding is given. Then you should find out numerical aperture and angle of acceptance. So numerical aperture, we know the equation, that is square root of n1 square minus n2 square. So then we are getting 0.244. Then angle of acceptance theta equals a sine inverse of numerical aperture. So then we are getting 14.1 degrees. So then the seventh one, 7a, that is set up one-dimensional time independent Schrodinger's wave equation. So you can know, so you should write de Broglie's wavelength. So that is lambda equals h by p. So starting from de Broglie's wavelength, then we are writing the wave equation describing the de Broglie wave. So that is psi equals a e power I kx minus omega t. So here you should write all these derivation part. So up to d square psi by dx square plus 8 pi square m by h square e minus v into psi equals 0. So in this above equation, psi is the wave function, and then this e that is the total energy, v is the potential energy. So up to this you have to write. And then B question, that is mention the 3 modes of vibrations in CO2 molecule with a neat diagram and construction and working of CO2 laser. So what are the 3 types of modes in a CO2 laser? Okay, CO2 molecule. So there are symmetric stretching mode, asymmetric stretching mode, and then bending mode. So these are the 3 different types of modes for a CO2 molecule. And then for construction of the CO2 laser, so you have to draw a neat diagram, and then this discharge tube, that is of length diameter 2.5 centimeter and the length is 5 meter. Then you have to mention the tube is filled with a mixture of gases CO2, N2 and helium gases, and they are in the ratio 1:2:3. So you should highlight all these points. Then the pressure it is in the tube is 6 to 17 tars, and then the tube is closed by 2 optically plane mirrors. So one side is completely silvered and the other side is partially silvered. Then working of the CO2 laser, it is mentioned here. So here it is working on the principle of glow discharge of the gases, it is initiated. So this point you have to highlight. Then collision of the first kind, so you should explain E1 plus N2 equals, so what are these things you have to explain. And then how these nitrogen molecules are excited to the metastable state. Then the collision of second kind, that is N2 star plus CO2. So you have to explain these nitrogen molecules from the metastable state, they are coming to the ground state and they are colliding with the CO2 molecules in the ground state. Then CO2 molecules are excited to the higher state. Then you can see then the energy level diagram you have to do for nitrogen and also for CO2 molecules. So then you are supposed to mention population inversion is established, because after achieving population inversion only laser beam is produced. So you have to mention this point, population inversion, that is between the energy level E5 with respect to E3 and E4. Then transition from E5 to E4. So due to that, the laser beam of wavelength 10.6 micrometer is produced here. It is in the infrared, far infrared region. Similarly, the transition from E5 to E3. And here also the lambda value we are getting 9.6 micrometers. Okay, so the laser beam of wavelength 10.6 micrometer and also 9.6 micrometers is produced here. Right, so these readings you have to mention properly. And then 7th C, that is regarding laser, a pulsed laser beam, it is photons of wavelength 780 nanometers, it is given here. Then here we have to find out the number of photons. So you write this equation, n, number of photons it is in each pulse, that is n equals. So we can apply this equation, energy of each photon, that is E equals h nu and nu equals c by lambda. So lambda, that is 780 into 10 power minus 9. So then we are getting the E value 2.55 into 10 power minus 19 joules. So then energy of each pulse, that is E equals power multiplied by time. So power value it is given here in the problem, it is mentioned. Then we are multiplying by the time. Okay, so that is 10 nanoseconds. So then E value we are getting 2 into 10 power minus 10 joules. So then we are writing the equation, if n is the number of photons in the pulse, then n multiplied by delta E equals E, energy. So therefore n equals, then we are writing all these data here. Then number of photons we are getting as 7.86 into 10 power 8. So then the 8th one, that is prove that electrons cannot exist inside the nucleus of an atom. So here first you are supposed to write the energy of the body, that is E equals p square by 2m. So here this concept is proved, electrons never exist in the nucleus, it is proved with the help of Heisenberg principle only. So you are supposed to write the Heisenberg principle, delta x delta p, it is greater than, that is multiplication of delta x and delta p is greater than or equal to h by 4 pi. So then delta p we are writing here, then delta x, that is the radius of the nucleus, it is less than or equal to 10 power minus 14 meters. So then delta p we are getting 0.5 into 10 power minus 20 newtons. So then this value we are substituting in equation 1. So then the energy of the particles in the nucleus we are getting is, it is greater than or equal to 85 mega electron volts. So from this it is understood, if an electron has to exist in the nucleus, its energy should be greater than or equal to 85 mega electron volts. But during the radioactive decay, the energy of the beta particles is only 3 to 4 mega electron volts. So from this it is understood electrons never exist in the nucleus. So it is proved with the help of Heisenberg principle. Then the next one, that is regarding the Einstein coefficient derivation. So for Einstein coefficient, so first you have to do all these figures, how that rate of absorption is take place. Okay, absorption process, emission, spontaneous emission process, stimulated emission process. So that energy level diagram you have to perform. With that only you have to explain, give the definition, what is the definition for absorption, spontaneous emission. Then you write this equation, rate of absorption, rate of spontaneous emission. Okay, so then you continue with the equation, and here it is at thermal equilibrium, rate of absorption equal to rate of spontaneous emission plus rate of stimulated emission. So then we are substituting all these given data here. Then Planck's law you have to mention. Okay, so then we are comparing the equations. After comparing the final equation, you continue the derivation, all the steps you have to write. Then up to u nu equals a by b multiplied by e power h nu by kt minus 1. So up to here you have to write. So then 8c, that is an electron is bound in one dimensional potential well of weight 1 angstrom. Okay, and then the infinite wall and the height it is given here, infinite height. Find the energy value in the ground state and also in the first two excited states. So as per quantum theory, the energy eigenvalues it is given by En equals n square h square by 8m L square. So here n is the that energy levels, it is mentioning the energy levels, and h is the Planck's constant. So m mass of the electron and L it is given in the problem. Okay, so first we have to find out the energy value in the ground state. So for the ground state n equals 1. So we are getting E1 as 37.64 electron volts. Then for the first excited state n equals 2. So E2 equals, we are getting 4 multiplied by E1. So E1 equation here we are writing, then E2 we are getting 150.54 electron volts. Then E3 also, for E3 we are getting 338.7 electron volts. So then the ninth one, that is assumptions of quantum free electron theory. So here it is given here. Okay, so 4 points it is mentioned. Energy values of the conduction electrons are quantized. So write all these 4 points. Then the merits of quantum free electron theory it is asked. So that one also, so you know that temperature dependence of electrical conductivity. So for metals, if temperature increases, the conductivity decreases. So it is explained, it is explained by quantum free electron theory. Okay, so in detail you have to write all these steps. So sigma is inversely proportional to the temperature, and then the electrical conductivity and electron concentration. So as per quantum theory, equation for electrical conductivity, sigma is the electrical conductivity, equals ne square by m star, so multiplied by lambda by Vf. So Vf, that is the Fermi velocity, right? Lambda is the mean free path of the electrons. So this one also, all these theory part you have to explain in detail. And then 9b, that is regarding the Hall effect. So definition for Hall effect is given here, and then the derivation for Hall voltage. So here also you are supposed to do the neat diagram, and then you start the derivation, that is Lorentz force Fl, and then the Hall force Fh, then in equilibrium Lorentz force that is equal to Fh. So all these steps you have to write. Then here at last we are getting the Hall voltage Bh, that is equal to Bi by rho W, rho multiplied by W with. Okay, so RH, that is the Hall coefficient. So Hall coefficient that is equal to 1 by rho. Then the one problem is given here. So 9c, that is the find the temperature after which there is 1% probability. Okay, so that problem it is given. So f of E is given, that is 1%. So that is 1 by 100 only. That is equal to 0.01. And here E minus EF value it is given, that is 0.5 electron volts. Electron volts it is converted into joules. So here you write the equation Fermi factor f of E, that is given by equation 1 by 1 plus e power e minus ef by kt. Then from here we should find out the temperature value. So you bring the temperature term to the left side. Okay, so at last you can see the temperature term, it is brought to the left side. Then natural logarithm is taken on both sides because it is as exponential. So for that we are taking natural logarithm. Then we are finding the temperature as 1261.1 Kelvin. Then the next one, that is 10a, that is polarization. So it is regarding what is polarization. So polarization definition, first you have to write. So polarization in dielectrics, so that is the displacement of the charges in the presence of the, so due to the applied electric field. Okay, so that definition you have to write. Then different types of polarization, that is electronic, ionic and orientational polarization. So then in detail you have to explain all these steps. Okay, so all these things you have to explain with the diagrams. So electronic polarization, that is polarization which happens in the non-polar dielectrics. Similarly, orientational means the polarization which occurs in the polar. Ionic polarization, the polarization which happens in the ionic solids. So with neat diagram you have to explain in detail. Then the Fermi energy derivation. What is Fermi energy? So Fermi energy definition you are supposed to write. And then you have to mention this equation also. Derivation part you have to mention. Derivation for Fermi energy at 0 Kelvin for a metal. So up to this equation EF naught, all the steps you have to write. Then up to EF naught means Fermi energy at 0 Kelvin, that only EF naught, that is equal to h square by 8m multiplied by 3n by pi power 2 by 3. So up to here you have to write. Then the problem, one problem is given here. The resistivity of intrinsic germanium is given. So you can see here. So here resistivity that is mentioned by rho equals 0.47 ohm meter. Then electron mobility mu e, and then hole mobility mu h is given. So here the question is carrier density Ni we have to find out. So Ni equals 1 by 1 equation it is written here. So already we know the equation. Resistivity in the left side you can see resistivity, it is inverse of the conductivity. So conductivity equation for semiconductors it is written here, that is Ni into E multiplied by mu E plus mu H. So here we have to find out the Ni only. So Ni is brought to the left side. Okay, so then in the right side you can see the same equation we have written here. Then we are substituting all the given data. Then Ni we are getting 2.37 into 10 power 19 per meter cube.